Chapter 6 of MYP4 Unit 2 is called Quadratic Graph Transformations. Now, we're familiar with the previous unit with the function y equals x squared, so it has that sort of parabola shape. And this unit, or this chapter of this unit, is asking what happens if we slightly adjust that function. How will it change the graph? So, for example, if the graph of y equals x squared looks like that, what if we did the graph of y equals x squared plus 3? How would that extra plus 3 change the graph? So the first thing that we had to do was to make tables of values for y equals x squared plus 3, y equals x squared minus 3, y equals x plus 3 first and then square the answer to that, and y equals x minus 3 in brackets first and then square the answer to that. So we had to do tables of values for all of those, looking like that. So x from minus 5 to 5, for example, and then work out what y would be for each of those and make the graph. So you're looking to do 4 tables of values and 4 corresponding graphs and see what those graphs look like. So if you haven't done that, I suggest you have a go at that now. So I hope you did that, and so you should have done something like that, 4 tables of values. And those are the actual values you get when you work them out. So obviously I won't go through that now. I hope you've already tried to do it, and if you didn't get the numbers there, do ask me in person for help. So looking at the graphs you get from that, there's the original graph of y equals x squared, and then if you do the graph of y equals x squared plus 3, you find that the whole thing is shifted up by 3 units. So generally, if you've got some function of x, then adding some number to it, like a, then shifts it upwards by that many units, by a unit. So taking x squared and adding 3 to it shifts it upwards by 3 units. And then we did x squared minus 3, and perhaps unsurprisingly now that shifts it down by 3 units. So generally speaking, if you've got y equals some function of x, then subtracting some number from it, so f of x minus a, shifts it downwards by that many units, shifts it downwards by a units. So in this specific answer, if you start with y equals x squared, do the graph of that, and then work out y equals x squared minus 3, it shifts the graph down by 3 units. Now the next one is perhaps more surprising. So when we did x plus 3 squared, so x plus 3 in brackets and then square that, and we did the table of values, what it did to the graph was shift it towards the left. So in fact, instead of cutting at where x equals 0 here, or instead of touching where x equals 0, it touches at where x is minus 3. So the fact that it's gone to the left and touched at minus 3, even though we added 3 to the original x, sometimes surprises people. Okay, so doing something with the x first before you apply the function, in this case squaring it, has the effect of shifting it to the left or the right. So adding 3 shifts it 3 units to the left, and not, as you might expect, shifting it to the right. And then you've probably guessed what happens next. If you subtract 3 from the x first and then square it, it shifts it to the right. So generally speaking, if you've got some function y equals f of x, and then you subtract some number from the x before you apply the function to it to get y equals f of brackets x minus a, then it shifts it to the right by a units. It's perhaps not everybody's thing to be able to remember all of the abstract notation like that, but if you can remember it in these terms, doing something to the x first and then applying the function shifts it to the left or the right, and possibly in the opposite direction to what you might expect. So x minus 3 is making the graph go kind of forward, if you think of to the right as being forward, by 3 units. So exam questions sometimes ask you to sketch a graph by considering transformations in relation to the graph of y equals x squared. So sketch the graph of y equals x squared plus 6x plus 14 by first writing it in the form y equals x plus a all squared plus b. That looks complicated. It's a bit like completing the square that you did in the quadratic equations unit previously. So it's kind of taking bits away in order to make perfect squares. But let's have a look at it. So start off with x squared plus 6x plus 14. Now I'm taking the coefficient of x, which is 6, halving it to give me 3, and then squaring that to give me 9. So instead of x squared plus 6x plus 14, I've rewritten the 14 as 9 plus 5. And I'm getting the 9 from half the coefficient of x squared. So half the 6 is 3, square the 3 is 9. So you can see how that's a bit like completing the square, where you get half the coefficient of x squared. And the point of that is that x squared plus 6x plus 9 is a perfect square, so you can rewrite it as x plus 3 all squared, getting the 3 from either half of the 6 or the square root of 9. So the whole thing can be rewritten as x plus 3 all squared, and then don't forget plus the 5 on the end that was there. So you can see how that's hopefully like completing the square, and you might want to go back and revise completing the square just so that you're familiar with it. So what's the advantage of that? Well, writing it this way, we know what the graph of y equals x squared looks like. We know that the graph of y equals x plus 3 squared will just be a horizontal shift. So having the plus 3 before we square the x will shift the graph 3 units to the left. And then having the plus 5 on the end, we'll just take that graph and shift it 5 units up. So starting with the basic y equals x squared, then shifting it 3 to the left and 5 up will give us the graph of this thing, which is the same as this thing, x squared plus 6x plus 14. So if we do the graph of y equals x squared plus 6x plus 14, we expect it to be the same as the graph of y equals x squared, but shifted horizontally and vertically in that way. So I actually did that on GeoGebra, and lo and behold, the graph of y equals x squared plus 6x plus 14 was like the original graph of y equals x squared, but shifted 3 to the left and then 5 up. So instead of bottoming out at 0, 0, it bottomed out at minus 5, 3. So here's a question. By rewriting y equals x squared plus 7x minus 18 in the form y equals x plus something squared plus b, find out where the vertex of the graph is, so find out where it bottoms out. And then question 2, by factorizing y equals, or by factorizing x squared plus 7x minus 18, find where it's equal to 0. And then from that, sketch the whole graph. Okay, that is tough, so have a go at that if you can, and this is kind of meant to be a challenging extension part of the unit, but do have a go at it if you can. So there it is, y equals x squared plus 7x minus 18. Now, by the way, the minus 18 on the end tells us it's going to cut the y-axis at minus 18, because when x is 0, y will be minus 18. So that's telling us something about the graph. So I've got minus 18 here. I'm going to try and take the coefficient of x, which is 7, halve it, which is 3.5, and square that, which is 12.25. So from that, I'm going to rewrite minus 18 as 12.25 minus 30.25. The advantage of that is that x squared plus 7x plus 12.5 is a perfect square. It's x plus 3.5 all squared. You can easily get the 3.5 from half of the 7. So that whole thing is the same as x plus 3.5 all squared minus 30.25. So that tells us that the graph of that is going to be like the graph of y equals x squared, but shifted 3.5 to the left and 30.25 down. So it will have a vertex at minus 3.5 and minus 30.25. And then question 2 was to factorize it. And when you factorized it and put it equal to 0, you got x equals minus 9 or 2. So that tells you that the graph will cut the horizontal axis at minus 9 and 2. So that's telling us all sorts of things about the graph. It told us these 2 points where it cut the horizontal axis. It told us the point where it cut the vertical axis, and it told us the vertex where it bottoms out. So all sorts of things to enable us to sketch the graph accurately without any need to plot individual values. That's all extension work, so don't get in a panic about not understanding that particular bit. It's only aimed at a couple of people, really.